could. I could just record the whole conference and speak.
I bet you can fix all that.
Let me have a look.
It's
mathematical, probably.
yeah, it's algebra. It's some ridiculous algebra.
It's pretty much
Yeah,
numerical
over.
manipulation.
And I'll have a look for stuff.
Here's the first page, and
Yeah.
another one.
You want to go from the part circled in pencil to
This equation.
this and tell us how.
Ignore the 2a.
Ignore the 2A.
2a is not met. It's
No.
part of the
Oh, yeah.
above it.
Okay, so you have negative
Yes,
dimensions,
that equation is-
plus or minus 30 dimensions.
All right, was everybody able to pretty much do the homework?
Yeah.
Yes.
Yeah.
I know some of you had issues with submitting it, but gave me hard copies, and that's fine.
I did. I couldn't do my login since I just made it crap analysis.
Okay.
So
So one comment, I put a note on the Angel page. For some reason, Angel is not accepting the .circ files
yeah.
when you send them in. It's accepting them, but it's not letting me look at them. And I think it's a file extension thing, because if I change it to a .txt, it works fine. And JPEGs and PDFs are going in fine. So if you submitted a .circ file through Angel, I'm going to ask you to either resubmit it after renaming it to a .txt or just email it to me. Okay, and maybe I have like weird things on the top there.
I got the IRC file to upload.
Well, it'll upload. It'll upload, but and when I look at it in Angel, it's got the right file size. But when I try to download it or to view it, it gives me a Microsoft error. It says file does not exist or is not available or something.
I bet you it's trying to open it in something else.
Yeah, but I also tried just right-clicking and saving. And it saves it, but when I look at it, it's got the HTML for a web page from Microsoft that says the file does not exist. Check this Microsoft help topic for more information. It's weird. But like I say, if I tried with a .txt, exact same file, it works fine. You can save it exactly what you expect. So, I'm not sure what the deal is, but
You want it emailed to you.
whatever's easier for you, go ahead and email it to me, or change the extension name to .txt and put it up through Angel. Either is fine. And just try to do that as soon as you can. I'm assuming nobody anticipated this and is going to try to do this at the last minute. So
What's the extension again? Dot C?
it's normally a .circ like circuit.
Okay.
CIRC.
So you want us to email you the circuit file or?
Yeah.
Can you go back to the slide with the email on it?
Yeah. So yeah, just some general notes. Cert files don't load. There's my email address. You can email it to me there. That should be fine. I'm not going to get to grading these until the weekend anyway.
Would you like it, Logisim has a option to export as a image. Would that be okay?
No, because then I can't simulate it. That's just a picture of what's on the screen,
Okay.
which is good if you're trying to document your circuit. But I actually need the .circ to be able to run it.
And it was the CIRC you're having problems with, or the text files?
Just the CIRC. Text files are fine. PDFs are fine. JPEGs are fine.
So you wanted us to change the CIRC to TXT?
Yeah, if you just change the name of it to .txt, it seems to work, which is why I think it's like some kind of antivirus filter from the 80s or something.
There's something weird about those files because when I went in, the first time I did it, I forgot to do the 7-segment display.
Mhm.
So I just went on it and tried to open it, but I had to run, and I don't know if anybody else had this, but I had to run the executable file again for it to even
Right.
find Augustine that didn't like.
Yeah, those circuit files, I think they're just XML files. So it's like plain text, and it's the standard extensible markup language format. And there's already something probably associated with an XML file.
So I could have just opened it and texted it or something.
Yeah, probably, although, as it is, when I get a Windows file, I need to like get rid of the control M's on the end of each line sometimes, so it's a little weird. But email seems to work, but like I say, if it's easier to use Dropbox, feel free to do that. Just change the extension name, and I think you can change it to JPEG or PDF or anything else. It's just CIRC for some reason. Maybe it's the 4-letter extension is freaking out Windows. I don't know. Okay, so get those to me as soon as you can, and I'll grade them along with the rest of the assignments. Reminder: the midterm is on the 29th. My videotape last class seemed to work. The quality is great in the original MP4 file, but the compression is kind of killing it. So if you want a 2 GB version of the file, give me a thumb drive.
I brought one, but
Yeah.
I definitely.
Okay. And this last thing, if you're in town and you're bored the day before Thanksgiving, I'm going to be doing a seminar up at Portland State University as part of their Nuts and Bold Ideas series. And the idea is to present 10 minutes of some novel research idea, and then everybody just kind of brainstorms about it and picks it apart for the next 40 or 50 minutes. Very, very brainstormy kind of free-flowing exchange of ideas. And they invited me to come up and give a talk. So I'm giving a talk on artificial matter, that was one of my dissertation proposals that people thought might be a little too wacky to get signed off on. So it's a pet project, but it's the idea of engineering extremely small sort of artificial atoms that you can put together to build artificial matter with whatever properties you want, to be able to control the molecular properties of it, to be able to build something that's very stiff or flexible or malleable up to a point, and then yields or things like that. And then to be able to create dynamic materials out of this, so materials that like shape shift in real time, so you have your dining room table that turns into a sofa when you're done eating, things like that. And has implications for like green manufacturing, because when you're done with these things, you can just give them a command and they'll deprogram back down to these constituent artificial atoms, and you can use those to build something else. So I'm going to be doing that. Should be weird and fairly controversial. So.
Like, what would you make the artificial atoms out of? More like other atoms? Because then it's not really all that artificial.
They'd be little electromechanical systems. So I mean, if you're familiar with any of the work going on in MEMS, micro electromechanical systems, there's a famous picture of a ant holding a little gear in its mouth. That's part of a MEMS system. So you can manufacture these extremely tiny machines. Go on YouTube and look up MEMS or nano gears or things like that. You can find all kinds of bizarre stuff that people have built. And you build these things largely by manipulating individual atoms. You can actually, with the right kind of equipment, push individual atoms around. IBM did something years ago where they took, I think, 35 xenon atoms on a nickel plate, and they pushed them around to form the letters IBM, and took a scanning microscope picture of it. And it's like atomic scale manipulation. So you build these little machines with control systems in them, similar to the state machines we're going to be talking about today, and have an ad hoc communication network so that when they're in proximity to one another, they start communicating, and you sort of build up from there. So it's tied into what my research did end up being on, but in a different direction. Thank you.
Seriously.
No.
Well, like we're running on both.
Okay, that's fine. I'll keep them together.
No staple, -1.
Oh, he took up points for the roughly things and then let it.
Oh, yeah.
That's hard.
Oh, our math teacher,
He does that. He actually
Nuts.
does do that.
Really?
Yeah,
nuts, I tell ya.
he's crazy.
He's cool.
Crazy is a good combo. All right, so those are the basic announcements. Reminder, this is on the website now. We put it in this lecture too, in case you want to find it. It's also under the main lecture things, our approximate schedule. Yeah.
Question about your thing at Portland State. If
Yeah.
we are going to be out of town, are you going to videotape that thing?
I might videotape it, yeah.
That'd be cool.
I've taped some of my other talks up there. They seem to be okay with that. Thank you. So yeah, I'll try to do that. Because it should be interesting for me to like go back and look at later. Because like I said, I think these things are kind of like free-for-alls. Thanksgiving. So, if you look up Nuts and Bold Ideas, you can see all the other seminars they're doing. They get into some weird things. I mean, they're just all over the place. It's not just engineering, it's economics and philosophy and all kinds of things. It's a cool seminar series. All right, we'll talk about the homework next week after I get a chance to look through it. So if there's no questions on the homework or anything so far, okay. And yay me, it's my birthday.
Happy birthday.
All right, so today we want to talk about finite state machines. And these are basically sequential circuits built out of flip-flops and latches, as well as combinational circuits. And finite state machines are useful for a lot of different things. They're useful for basic control systems, so you can build controllers for elevators or traffic lights or pinball machines. You can do parsing with them. You can take in a set of text and analyze its syntax and tell if it's syntactically valid. A lot of work in natural language processing, things that are supposed to read text and come up with a meaning of it or determine some fact from it, are built on finite state machines. And there's a lot of linguistic work that is very similar to what we do in FSMs. And if you go inside your computer and you find a Pentium chip, and you go inside the Pentium chip and you find the part of the CPU that's doing everything, that's a state machine. Okay, so this is going to be what we use for the rest of the course when we start designing computers and the data paths and building systems that can do the fetch, decode, and execute cycle that makes computers run. So this is central to most everything else that we do in this class. So it's good stuff. The basic goal of a finite state machine or a state machine, they're finite because they only have a fixed number of states, so you can actually build them. The basic goal of a state machine, you want some way to methodically respond to not only your current inputs, but to things that have happened in the past. Okay, basically past inputs. And as a simple example, we'll work with this one for a little bit. We can imagine a machine that has 3 states, okay, and we just call these states 0, 1, and 2. They're just different conditions that this machine can be in. And we assume this machine accepts 3 inputs, A, B, and C. Okay, so those are the only 3 characters you put into this machine. And at any time, it's in either state 0, 1, or 2. And you can create this state table that describes how this machine responds. Okay, so it's like a truth table, but it has to know more than just the inputs. It has to know what state the machine is in. So it's the same design as a truth table. You list the present state. So if it's in state 0, there's 3 possible inputs, A, B, and C. And for each of those, the machine may perform some action, which I'm just calling with letters here, X, Y, and dash means it doesn't do anything in particular. And after performing that action, it enters another state, given by the next state column. So if this machine starts in state 0, and I feed a B into it, what's the next state going to be? It's going to go into state 1. If it's in state 1, and now I feed an A into it, it's going to jump to state 2, okay, and it's going to output it. It's going to do some action W and go into state 2. And state 2, I might start feeding in a bunch of A's and B's and A's and B's, and it's just going to keep staying in state 2 until I feed in a C. And then it'll take some action U and jump back to state 0.
It's like Picobot.
Yeah,
Yeah.
I was just thinking that.
same thing.
And you can use state machines to make simple control systems for robots that are going to like move themselves through a maze or try to do line following or things like that. Okay, the control systems for those are usually simple state machines, and you can build them with the techniques that we're going to talk about here and how you take this and transform it into a circuit. So you bump into these things all the time. Now, an interesting question comes when you add a new state called a halt. Okay, and the idea is this machine, if it ever enters a state that we call halt, it stops. Okay, it's like a halt instruction on a regular computer. It stops, nothing else happens. Okay, it ignores all other input. And so an interesting question is, if you have a state table like this, and there are halt states somewhere in the table, and you know that you're starting at stage 0, and you know what your particular set of input is, does this machine ever halt? Okay, that's a perfectly reasonable question to ask. It's an extension of a more general question, which is if you take any program written in any language, you know what the program is, you know what the input is, just look at them and answer the question, will this program ever stop? Assuming there's a stop statement in the language. Or will it run forever? If you give it a C, if you have some way to get to state 2 based on the input you have. Now, if you have a particular set of input, you can trace through it. You may eventually get to a halt statement, but what if you trace through it for 100 years? Yeah, so it's a hard question. How do you look at this table and look at a set of input and say, does this machine ever halt or not? That's an interesting question. So this is a bit of a side note, but this is something that anybody in computer science or engineering should probably know about. So we're going to take a side note here. Whitehead and Russell, they were, I don't know what you would call them, but in the beginning of the 20th century, early part of the 20th century, they were working on an ambitious project. But back then, the really smart people, they kind of did everything. So these people were dabbling in mathematics, they were dabbling in logic, philosophy. Russell, in 1950, won a Nobel Prize in literature. So these people were kind of all over the place. Early part of the 20th century, they were working on an ambitious project. What they were trying to do was take mathematics and make it extremely rigorous, put it on a completely solid, logically based footing. And their idea was to do two things. One was to define a set of axioms, and the other was to define a set of rules of inference. Okay, so in a mathematical system, do you know what axioms are?
They're the statements that you say are true, and you build theorems off those.
Right.
And they're just sort of assumed to be or asserted to be true without backing them up.
Exactly. So they're things that you simply state are true. You don't prove them, you don't derive them from anything, they're your starting point. Okay, so in geometry, there's usually an axiom, two parallel lines never meet. Okay, that's not provable, but it's one of the assumptions that we make. So that's one of the axioms, and from there, you can build up a mathematical system. And rules of inference are how you build up that system. You start with your axioms, and these say how you get from one set of true statements to another set. Okay, so if you have your axioms and you have your rules of inference, you can start proving a number of other statements, and you can build up an entire mathematical system. So they wanted to do this with arithmetic, okay? And we know certain things about arithmetic. We know that 2 equals 2, but how do we know that? I mean, every time we find 2, it's equal to 2. 2 apples and 2 oranges, we always have the same number of pieces of fruit. But how do you prove that? Or is it an axiom? So they wanted the smallest number of axioms possible, and then a way to prove everything else. And they set about this, and they worked for a long time, and they came up with multiple volumes of things that looked like gibberish. And it was called Principia Mathematica. And it was this completely rigorous restatement of arithmetic. And so in the first volume on page like 379, they have all these weird looking symbols and a note that says from this, once they define addition, then they'll know that 1 plus 1 equals 2. Okay, that's like 400 pages into this. And it's not until volume 2 that they actually showed this was true, because then they defined what addition was. So they came up with all of this stuff, and it's wonderful to look through. I mean, these people were just like so deep into this. In 1931, someone ruined their party. Okay, a guy named Kurt Gödel came along, and he came up with a wonderful mathematical proof that basically showed that what they were trying to do was impossible. So here's what he said. He said that if you define a set of axioms and rules of inference, and you develop a system based on that, there's exactly 2 possible things that will happen. Okay, one thing that might happen is you don't have enough axioms. And there's going to be some things that you cannot prove and you cannot disprove. In other words, things that you would need to either accept or reject on faith. But you cannot get to them from the axioms you defined and from the rules of inference. That's one possibility. Okay, that's called an incomplete system. The other possibility is that if you add enough axioms so you can prove everything, you're going to have inconsistencies. There will be at least one statement that you can prove is true, and you can also prove is false. And that's it. Those are the only possibilities. There's no sweet spot in between. Either you don't have a complete system and there's things you can't prove, which is annoying, or you can prove everything, but you've also got contradictions. You can prove that 1 + 1 = 2 and 1 + 1 does not equal 2, for example, which is equally annoying. And that should bother you. Okay, that's not a statement about a particular version of geometry or arithmetic. That's a statement about sort of knowledge itself. Not even human reason, sort of about the knowledge itself. And that's disturbing. That disturbed a lot of people. It definitely disturbed Whitehead and Russell. But that's something he proved, and it's a wonderful proof. So that was 1931. Now, around that same time and shortly after, people started working on this idea of the halting problem. If you have an algorithm and you have a set of input, does it ever halt or does it run forever? And Alan Turing was one of the people who did a lot of work on this. And to study this problem, he created this theoretical machine called a Turing machine. And a Turing machine is basically a finite state machine. Okay, the same idea. It has a notion of states and a transition table and inputs and next states. And in studying the halting problem on Turing machines, he concluded that the halting problem was undecidable. If you have a program and you have a set of input, it may be impossible to tell whether it halts or not. And that's really weird, I think, because if you run this program for a year and it halts, you've answered the question. The fact that it's undecidable means it can't halt after a year. Otherwise, you'd have an answer. And it can't halt after 10 years, because if it did, then you'd have an answer to the halting question. And so there are programs out there that you can run for 1,000,000 years and they'll never halt, but you still can't say it's not going to halt tomorrow. Okay, so there's something weird in there. Okay, hopefully that disturbs you a little. So he develops the Turing machine as a way to study this. And Turing machines are computationally complete. Anything you can run on a Pentium, you can run on a Turing machine. And anything you can run on a Pentium, you can implement as a state machine in general. Okay, I mean, Pentiums are just fancy state machines, basically. Alan Turing is an interesting study. He did a lot of work related to computers as we know them today, the idea of a stored program, which we'll see later. Okay, so back to our first example. Here's a transition table. A useful way to study this is to draw what's called a state diagram or a transition diagram. And it's just a picture. And basically you have your 3 states. We'll call them 0, 1, and 2. And what you want to do is for each state you want to indicate what other states it can change into and under what conditions. So if we get an A, we move from state 0 to state 1. So I would draw an arrow from 0 to 1, and I put the label A in the beginning. Okay, and that just says that's when you move from 0 to 1. If you have state 0 and you get a B, you also go from 0 to 1, so I'll put another arrow there. And if you're in state 0 and you get a C, you stay in state 0. I'll just do that like this. And you can go through a transition table and you can draw this whole picture. You go from 1 to 2 if you get an A. And you go from 1 back to 0. I'm just going to use commas B or C. And from state 2, you have an A or B, you stay in state 2. If you have a C, you go back to state 0. Okay, and that's equivalent to that. I haven't shown the actions that take place here. You can indicate those along the arrows if you want. Okay, so I'm gonna ask you to go back and forth sometimes between state tables and state diagrams. So be comfortable with that. Just a different form of representing the same information. Okay, so there's a fancy drawing of it. And I did indicate the actions here. So for me, I just kind of put the actions in quotes halfway along the arrow. So that just shows you transitions. I renamed my states S0, S1, S2, because it'll make the next part less confusing. Okay, so suppose you want to build a machine that performs these state transitions. How are you going to do that? Starting with the state table or the state diagram. Basically, you can write Boolean equations corresponding to that state table, just like you wrote Boolean equations for truth tables. So you can look at what the next state is and write an equation describing when you get into a next state of, say, 0. So state S0 comes from either being in state 0 and getting a C, okay, which is this condition here, or the third line from the bottom being in state 1 and getting a B or a C. So state 1 and B or C. Or that last line if you're in state 2 and you get a C, and your next state is state 0. Okay, so this is what the next state is in terms of the current state and the current input. And likewise, S1, you can define the 2 conditions where you move into S1, and the 3 conditions where you move into S2. And if you have a system that implements those 3 equations, then each time you get a new input, you can look at your current state and figure out what your new state is. And that's basically like the sum of products that we were doing to convert truth tables into equations. Okay, so why do you want state machines? Some of the things you can do with them, you can do basic logic operations. So this first table up here, this is a table that corresponds to an AND function. Now this is an expensive way to do ANDs, but starts in state 0, and if you get a 1, it's going to stay in state 0. And basically, as long as you keep receiving 1s, it's going to stay in that first state, S0. As soon as you get a 0, it's going to move to state S1. And once you're in S1, it doesn't matter what you get, it's going to stay in S1. So what is this doing? It's saying, if your input looks like 1, 1, 1, 1, 1, 1, all of these you're in S0. As soon as you get a 0, you jump into S1. And it doesn't matter what you get here, you're always in S1. Well, that's doing a logical AND on your inputs. Okay, it's saying that up to this point, the AND of all my inputs was still a 1. Okay, S0, we're outputting a 1. As soon as you find a single 0, now the AND of your input string is 0. And it'll be 0 forevermore. Okay, so that does a logical AND operation. This is similar, it does an OR. You start in S0, and as long as you input zeros, you stay in S0, which means the OR is 0. First time you get a 1, you change to S1, which means the OR is 1. And same thing. As soon as you get this, you know that the OR of all your input bits is a 1. Doesn't matter what comes next. Okay, now that's a weird way to do logic, but it's just an example. Is this making sense? Okay, you can do parsing. So you have a set of characters coming in A through Z, and you want to know if you ever see the string DOG. And here's a state table that will tell you that. So sometimes these are easier to analyze with a state diagram. So this is your initial state. If you get a D, you go to S1. You get an O, you go to So you're sitting there, you're getting in a bunch of characters, you get in an A, you get in a B, and a C. As soon as you get in a D, you go here, and this state means I've gotten a D. Your next character is an O, you go here, and that state means I got a D followed by an O. If you get a Q, that's not a G, you're going to go all the way back to the beginning. Okay, if you get a D and you go over here, and then you get an F, you go all the way back to the beginning. Okay, if at some point you get a D and you get an O and you get a G, then you say, I found a dog, and you go back to the beginning. Okay, it's a simple parser, but it's the same idea that you use in parsing extremely complex text. It's a way to pattern match, basically. And again, from here, which is where you might start, you can draw this state table, and from there you can draw equations that describe the state transitions, and then you can build hardware to implement that. We'll look at some hardware in a minute. Okay, so you can parse text with finite state machines. Here's a simple combination lock. Okay, this is a machine that's supposed to detect the pattern 101. Okay, anywhere in your input. So you're putting in ones and zeros. If you ever put in a 1 and a 0 and a 1, then you jump into state 3 and you take some action. You open up a lock, for example. And well, I'm wondering if I can rearrange this room at some point, because I would love to have that whiteboard. I was wondering if there's like some code somewhere that I'd be violating.
We went into one.
like this, so I'm not sure.
We went into one of my classes the other day, and all the tables were in these like random weird groups. And
Yeah.
they said, "Oh, must have been a teaching class because they're doing groups."
Right. I might do that, see if anybody notices. As I would. It would be nice to be able to get to that whiteboard.
Is that a whiteboard there and then put all the tables next to it?
Otherwise, why do we need it?
Okay, so pretty obvious. If you start in state 0 and you get a 0, button 0 is pressed. You just stay in state 0, it means you haven't matched anything. If you get a 1 and then a 0 and then a 1, you go to your success stage. Okay, which I'll just mark with a star saying like that's when we unlock the box. If you're in state 1 and you get a 1 instead of a 0, where do you want to go? You'd think you'd want to go back to the beginning, but in fact, if your input string is something like 1, 1, 0, 1, that still is a good match. That's a 1, 0, 1. So this state here means that we've received a single 1 so far. So if we're in state 1 and we get a 1, we can't go on, but we can actually stay in state 1. Which means button 1 has been pressed. And then when we come to state 2, if we get a 1, we complete. Here, if we get a 0, we know we want to go back to the beginning. Okay, so this means we haven't matched any of our string. This means we've got a 1. This means we found a 1, 0. And we found 1, 0, 1. And then once you're in state 3, if your next input is a 0, back to state 0, but if your next input is a 1, again, you want to go back to this state. Because you've matched the first character of your secret combination. Okay, so you need to watch that when you're making these diagrams for the tables. But that's a state machine that will implement this little 3-digit combination lock. And again, it's basically a parser, but it's a different kind of parsing because we're repeating characters. It's the same idea as looking for a dog. Okay, so there's the Boolean equations corresponding to that state table. And what if you want to actually build a circuit to implement this? Okay, so you want to actually create a piece of hardware that will do something when you press the 1 button, the 0 button, and the 1 button. So this is where we use these sequential devices from last class. So here's a circuit that will do that. So basically, we can use a D flip-flop for each state. Okay, we'll think of this as S0, S1, S2, S3. There's an output Q and there's an input D. And we'll assume these are triggered on the rising edge. Doesn't really matter for this example. And these outputs here, these Qs, tell you if you're in the corresponding state. If you're in state 2, you'll have a 1 coming out of this flip-flop and a 0 coming out of the others. Okay, that's what we're using these for. We're using them to hold the information about what state we're in. And so if we want to build a circuit that tells us when to go into state 3, we know state 3 is just the AND of state 2 and button 1. So we have some button 1 and button 0. If you take button 1, you take state 2, and you AND them together, the output of that is 1 exactly when you're ready to go into state 3. So what we can do is we can take this and we can feed it into the D input on the state 3 flip-flop. And now the idea is each of these clocks is going to be tied together. Into some master clock. So a clock is just a line that we can set to 1 or 0. Okay, there's nothing special about it. We call it a clock because it's generally changing regularly between 1 and 0. Okay, it's just another signal. And the idea is every time that we raise this clock from 0 to 1, we're going to transition from one state to another state according to what the inputs are. So if we're in state 2 and button 1 is pressed, the next time that the clock goes high, we have a 1 going into D, and that will cause S3 to get set. Okay, and we'll enter state 3. And we have logic feeding. We have logic feeding S2. Okay, S2 is S1, and it would be 0. So S1 and it would be 0. That feeds state 2. Well, if button 1 is pressed and button 0 is not, then when this clock ticks, this is going to be a 0. And so S2 is going to get cleared, and S3 is going to get set. And the machine transitions from state 2 to state 3. And so you build similar circuits for the input to the S0 flip-flop and the input to the S1 flip-flop. And every time you tick this clock, it transitions from one state to another according to that table. That's all there is to building a machine to implement this. And suddenly you've built a combination lock circuit. And then of course you can do something like take the output of that and send it to an unlock input on something you want to unlock. Alright, questions?
I'm trying to see how you connected your Boolean equations to that. Like, what does the Q go to with the first?
Okay, so here's the actual circuit.
I don't know. Yeah.
And it ignore this for a moment. There's the AND of button 1 with the output of state 2. Up there on the top is the AND of button 0 with the output of state 1. The input to state 1 is an AND of button 1 with this big long OR statement. And we're ORing basically state 0, state 1, and state 3.
Oh.
Okay, and that's that Boolean equation for state 1. State 0, state 1, and state 3 all ORed together and ended with B1. So I simplified it a little on the right there. And the input to button 0 is S0, 2, or 3, ended with button 0. And so we take S0, is that the one I just did?
Yeah. Using that.
Yeah, S0, S2, and S3, they get ORed together, come around the top, and they get ANDed with button 0, and that's S0. Okay, and you just kind of put it together from the equations.
What's with the double inversion down there?
Yeah, I was afraid you were going to ask me about that. So I didn't want to have a clock in this. What I wanted to do was any time that I pushed either a 0 or a 1, I wanted that to generate the clock. Okay. And I tried to do that just by taking the two push buttons and ORing them, and saying if you push either one, now your clock goes high. Okay. Well, there's a race condition in there, because the way I describe this, you don't want the clock to go high until you've already set the D value. Okay. Now to set the D value, you might need to go through an OR gate, and you might need to go through an AND gate, and then you need to get into the D input on the flip-flop. Whereas to set the clock high, all you have is an OR gate. That tends to happen really quickly.
So you're just throwing those.
So I'm slowed down.
for propagation.
Exactly. It's a dirty design trick, but it works. Okay, and I use 2 inverters, so I wouldn't change the value. And
Oh, look at that.
look, there's an actual circuit.
Fly the beard of Zeus.
Oh, it's really-
So if I input a 0, you can see I go into state 1. And as long as I keep hitting a 0, I stay in state 1. If I put in a 1, now I go into state 1.
Favorite game.
If I do another 0, I make it up to state 2. And if I hit another 0, I go back to state 0.
It's a combo.
It separates your wires, like the wires across it. Separate.
They're separate, yeah. If they get joined, there's a little dot there. But I'll warn you on this particular tool, if you move stuff around, sometimes things get connected
Yeah.
inadvertently.
Yeah, mine has like wires going around the edges so they don't cross over. So
Yeah.
no.
And I don't know how good the undo is. Does it undo those
Yeah.
pretty easily? Okay.
Yeah, I did a lot of undoing.
Yeah.
And if you just grab a wire and you want to like erase part of it, you just shorten it back up.
Right, yeah, I figured that out finally. That took me a while. Okay, so I mean, yeah, here's a combination. You hit a 1, make it to S1. You hit a 1 again, you just keep staying in S1. Okay, if you hit a 1, then you hit a 0, and then you hit a 1, that we matched. So we have
Hooray.
clocks.
What?
It's easy, right?
Yeah.
Totally.
Oh, I was just connecting that to something else.
Mm-hmm.
So is there some way that you could like automatically generate a state machine description from saying I want to parse this?
Yeah.
series?
There's tools out there that will take something like a state table and spin this out for you. Yeah, definitely. But don't use those. Yeah, I mean that's what's nice about all this stuff. The CAD tools out there do all this for you, but you still need to know. Well, yeah. You don't have them on the good terms. So.
Oh,
Good point.
it's not a fish.
I think you win that one.
Okay, so you can take any of these and you can build circuits that implement it. So as an example, traffic light controller. So this is a really simple traffic light system. Basically, you have an intersection, you have traffic flowing north-south, you have traffic flowing west-east. And the rules are very, very simple. Suppose that traffic is flowing west-east initially, and a car arrives on either the south or the north. Okay? If west-east light has not been green for at least 30 seconds, you let it stay green. Okay, because we want to get some traffic flowing. If the west-east light has been green for at least half a minute, and then a car arrives from the north or the south, or a car arrives before 30 seconds, okay, and then 30 seconds hits, then you begin to change the light. Okay, first you make the west-east light yellow for 5 seconds, and then you make it red for 5 seconds, and then you make the north-south one green. Okay, so we put a little lag in there to catch the red light runners. And then once north-south is green, we do the same kind of thing, but in the opposite directions. We require it to be green for at least 30 seconds. If there's a car waiting on west-east, once we hit 30 seconds, then north-south goes yellow for 5, red for 5, and then we switch west-east back to green. Okay, that's the basic operation of this intersection. And it's pretty clearly a state machine, the way I've written it. Very easy to describe. There's the transition tables, so I got creative with state names, so they would make a little more sense. West-east green new means that we just changed west-east light to green. Okay, west-east green wait means that there's a car waiting on the other road, but we haven't been green yet for 30 seconds. And then west-east yellow means it's yellow, red means it's red, and the same for north-south. And you can work through these. I'm not going to go through them all myself, but if you're in the new state and there's a car on north-south and you haven't hit 30 seconds yet, you just go into the wait state. And in the wait state, you wait until the timer hits. There's a timer in the system too that you can reset and you can monitor. If the timer hits 30 seconds, then you go into the yellow state. If a car shows up on the north-south road and you've already been green for 30 seconds or more, you jump immediately to the west-east yellow state. And you start doing that. In the yellow state, you reset the timer and you go to the yellow state. You just wait until the timer hits 5 seconds, reset the timer, go into red, wait until the timer hits 5 seconds, reset it, and then jump into north-south being green. And same in the other direction. Yeah, you can make it longer, and you can add sensors so that you see how much traffic there is, and to pick up people who do right on red so you don't change for them and all that. And it would just be more states and a bigger transition table, exactly the same implementation. We are flying through this material. Questions?
Wow.
I don't mean to suggest that it should make perfect sense at this point, but
I think it's fine.
if it's confusing what I'm talking about, okay, if it's not making sense, then we should talk about it. If it's not sunk in yet, that's fine, okay, you're going to have to work with it to actually click. The basic ideas hopefully are making sense.
Yeah.
Yeah.
Picobot.
I'm just glad we can finally use Picobot.
Yeah.
So tell me about Picobot.
Oh, it's a maze thing.
And yeah, you're like a block, and it'll be you'll be at any random spot, and it will give you the inputs are what walls are on your northeast, southwest,
Mm-hmm.
and pretty much it's pretty much the same thing, but you have to go through the whole entire maze, at least touching each wall area at least once,
Okay.
and you're done.
So what did you do this in? Did you implement this?
Yeah,
Oh.
it was.
We didn't implement.
We didn't really
We
implement.
made state machines that solve the problems.
Okay.
Like the
It was in the introductory programming.
yeah, we had to figure out step by step which way to go if there are certain walls in front of us.
Okay.
Yeah, so we just make like state 0 if the same wall is on your east. Yeah. Keep going north.
Mm-hmm,
If there's nothing there, then take a turn.
right.
And
So that's
then
always on your right.
Change it to state Wapiti.
Okay, yeah, yeah.
We did one like that was with animals, and then like different ones could fight each other different ways.
Yeah.
Yeah, and mine was awesome because after like 1,000 iterations, it would like start a sweeping pattern and kill everybody else.
Oh, cool.
So I won, but it was awesome. So you
Okay.
compete at the, it was our last one.
Cool. Yeah, there's a lot of work, especially there used to be a lot of work in state machines in terms of artificial intelligence. I mean, trying to make things that learn, because it obviously looks like, you know, sort of intelligent decision making that people do. And so there's been work in trying to build, you know, sort of intelligent acting systems based on state machines. And like I say, anything you can put on a Pentium, you can build a state machine to implement. And in fact, inside CPUs, it's just a big fancy state machine. So, there's some good programs in there. Okay, let me tell you a little bit about your homework, which I'm going to post this afternoon right after class. Well, when I get to it internet. This is kind of a long homework. It's worth 60 points. Okay, it's 5 questions. They may take you a while to do. Okay, it's time well spent. If you can get through this homework and understand it, you're going to have no problem on the midterm. Okay, because I'm not going to ask you anything harder than these. I'm probably going to ask you less ambitious questions. So it's time well spent. First question is pretty straightforward. It's just a weird looking flip-flop. Write me a truth table that tells me how this flip-flop acts.
Are those circles nuts?
Those circles are knots, yeah. And don't simplify it. Don't use De Morgan's law to change it around. Okay, work with it the way it is. And just show me a table A, B, X, Y. Show me what X and Y are for each of those. Don't call one illegal. Go ahead and show me what it does. And if these things don't change, just tell me they don't change. Just put down X or Y. If X or Y doesn't change, if it's a 1 or 0, put down 1 or 0. So same thing we did when we were analyzing like the SR flip-flop. Go ahead and just study that. So that's one problem.
Do you think that time clock would help with this?
Timing diagram?
Yeah. Timing.
Yeah, it might. Give me a table like this in the end, but writing a timing diagram might help you in analyzing it. Okay, but I want this as the final answer so I can look at it more easily. But yeah, feel free to do a timing diagram. Okay. Second one, you actually get to do a timing diagram. And these are clear in the PDF. They're not coming out very well on the screen. 3 toggle flip-flops. Okay, they're positive edge triggered. They're permanently enabled. Okay, so this green line here, one of those is going to the toggle input, and one of them is going into another input on the bottom. So they're just enabled. Okay, you can ignore this one going in here. Just think 3 toggle flip-flops, positive edge triggered, always enabled. There's a clock going into the first one, and the output of the first feeds the clock on the second. The output of the second feeds the clock on the third. And those 3 outputs come to these outputs, Q0, Q1, and Q2. And I just want to see what Q0, 1, and 2 do as the clock changes between 0 and 1.
Diagonally.
Diagonally. Ignore propagation delay. Okay, don't worry about showing me glitches. And there's the clock, and assume Q0, 1, and 2 all start off at 1, and just fill in the timing diagram, show me what each of those do. Okay, and you'll probably see a pattern when you start doing this. So do the first ones very carefully, and hopefully it'll make sense. All right, that's problem 2. Problem 3, state machines. So there's a transition diagram. I don't know why those are displaying so badly. Yeah. Yeah. So go ahead and draw the transition table for that diagram. Okay, and it should have a total of 12 rows because you have 4 states, 0, 1, 2, 3, and you have 3 possible inputs, A, B, and C. Okay, so for each state, each input, just figure out what the next state is, fill that in. Okay, problem 4, another state machine that has 2 input values, 0 and 1, and it's supposed to detect the pattern 0, 1, 1, 0, so a combination lock, but with a length of 4 without pattern. So 3 parts: draw the state transition diagram, draw the state transition table, and then write the Boolean equations for the next state, given the current state and the input. Okay, so same as the example we just did. All right. 5th one's a little uglier. So there's a state machine. There's a transition table for it. It has 4 states, which are labeled as 0, 0, 0, 1, 1, 0, and 1, 1. It has 2 inputs, A and B. So I want you to do 4 things. First, make a transition diagram. Okay, and if you do that in the right, if you position your states in the right way, it'll come out really nice and symmetric. Okay, that's a bit of a hint. 2, write the Boolean equations that correspond to that. Okay, and then 3, go ahead and sketch out, just on paper or in a tool if you want, the actual circuit that would implement those equations. So D flip-flops and a clock feeding all of them, and 2 buttons, A and B, and 4 states, 4 D flip-flops, and some combinational logic, whatever you need. Put together a circuit on paper that will implement this machine.
We can use Logicsim.
Yeah, you can use Logicsim, that would be great. I think that might actually make it easier because you can sort of try it out and see if it's working, and if there's something you're not doing right logically, it can help you figure that out. So, but you can turn it as a picture or do it all the way in Logicsim and turn that in. Okay. Question D, 1 pointer, do you want to use positive or negative edge triggered flip-flops and why? It's related to the propagation delay question. So, think about that. Make sense? All right, I'll post this probably when I get home because I still don't have internet here. I'll put it on the Angel site, and you'll have a week to do it.
There's never internet here.
So do next Thursday.
Yeah, do next Thursday.
Fun stuff. So like this next Thursday?
Not done. We got 15 minutes.
Oh, come on.
After this, are we gonna have another one for the midterm, or will this be the last one?
This will be the last one, and the midterm will stop here. Okay. What I'm going to do right now is start talking about arithmetic, and Tuesday will be a review. Thursday will next week will be arithmetic. So we will have a homework on that. Okay, but it won't be related to what's on the midterm.
It'll be good for
Yeah, probably that same Thursday. I'll make it an easy homework. Yeah, so next week we talk about arithmetic. We'll have some questions on that. Okay, so let me start talking about binary representation of numbers and arithmetic and things like that. And I expect this is going to go quicker than what I have up there. The first lecture we did here, we talked about representation of information and the idea that we use symbols to represent numbers or words or my name. I wrote this on the board and I said that's not actually my name, that's just a representation of my name, right? Because if I change that, my name is still Nick. And it's kind of weird that we have all these symbols that we use to represent different things, but they're all made of the same small set of characters, and it's just the order in which we put those characters means different things. Okay, it's a strange kind of hieroglyphics, where we just sort of arbitrarily assign meaning to certain orders of things. Wish I had a whiteboard back there. So with numbers, we do the same thing. We're all familiar with this. Okay, so in our normal representation of numbers, we have 10 symbols that we use, 0 through 9, digits, okay? They're base 10 digits instead of binary digits. And we build numbers out of combinations of those. Now, how do we do that? We use these to represent the numbers 0 through 9. And we want the number 10, we're out of symbols, so we need a combination of symbols. And so we create this new symbol, which is 2 digits, 1 and a 0. And we have this notion that this column represents the tens, and this represents the units. Okay, and we can do that with 20 and 30 and 45 and 56 and so on, up to 99. And after you've done 100 numbers, you're out of combinations of digits. So we create symbols with 3 characters. That's the hundreds, that's the tens, that's the ones. And if you have a number like 567, it's 5 times 100 plus 6 times 10 plus 7. Okay, we all know that. Binary works exactly the same way. And I know most of you already know how to write numbers in binary, but I want to put it on a standard footing. So we use 2 digits, binary digits, 0 and 1. And that's all we can write is 2 numbers. So if we want to write the number 2, we need a combination of digits. And so we write a 1, 0, and we say this is the 2's, this is the 1's. 1, 1. And now we're out of combinations of 2 digits again, so we add a 3rd digit. And this column corresponds to 4. And the idea is this is 1 times 4 plus 1 times 2 plus 0 times 1. Okay, so it's an exact extension of what we do in base 10. Each column corresponds to a different power of 2, 1, 2, 4, 8, 16. If there's a 1, we add that power. If there's a 0, we don't. And if you work it out, you get this order of numbers that we keep bumping into. Back to the idea that computers are really simple machines. They don't want to try to figure out right, you and I can look at that and we know there's 6 different numbers there. Okay, how do we do that? I mean, we have to process the visual field, we have to do some 2-dimensional processing, we have to know that this space is bigger than this space. It's a complex process, okay? Computers can't do that, so we make everything the same length. Okay, so we may say that all of our numbers are exactly 4 bits. And if you put zeros in, it doesn't change the value because it's just 0 multiplied by the power of 2. And so you can write out your numbers in binary like this, and the interpretation of them is exactly the same as in decimal. I made a comment the first day that this assignment of numbers to patterns of 1s and 0s, that's the only assignment you can make that lets you do things like mathematics, like arithmetic, like comparison. Okay, any other assignment and it falls apart. And that's specifically because of the fact that this pattern represents this arithmetic sum. Okay, and if you work through the details, you find that you can add binary numbers exactly the same way that you add decimal numbers. Okay, you just add column by column. And 6 plus 1 equals 7. Okay, so addition is exactly the same as what you do in the decimal case. Okay, so have people done subtraction of binary numbers? Okay. So when we subtract numbers, right, you subtract column by column, 7 minus 5 is 2. 1 minus 4 we borrow, so it's 11 minus 4 is 7. Borrow 1 from here, so it's a 1 minus 0 is 1. You can do the same thing with binary numbers, okay, but you don't really want to. Because we do something different in decimal numbers. If we did 45 minus 217, we get negative 172. Okay, we have this extra symbol here now. Okay, we don't have that in a computer. All we have is ones and zeros. So how do we deal with negative numbers? Sorry?
I was saying there.
Okay. There's a couple of things you can do. So early machines were like 8 bits, while the earliest machines were 4. Like the 8080 processor was an 8-bit machine. So you would take on 8-bit numbers. And 8 bits gives you 256 numbers to play with. So here's your 8 bits. And one thing you can do is you can treat this as a sign bit. You can say 0 is positive and 1 is negative. And so if you want to write the number positive 7, it looks like that. And if you want to write the number negative 7, you set that sign bit to 1. And it looks like that. And so this bit is just that extra symbol, that minus sign that we put in front of things sometimes. Okay, you can do that, and some computers have done that, but what happens when you try to add these numbers together? What do you get? I mean, if you add them bit by bit, you get like a 0, and a 1, and a 1, and a 1, and a 0, and a 0, and a 0. And maybe you get 1 over here, which is like negative 14 or something. Okay, and that's not good. Because what you're really doing is you're saying, I want to take 7 and I want to subtract this number from it. Okay, that's what adding negative 7 means. And when we write our number like this with this extra bit out here, we're no longer sort of sticking to that power of 2 kind of thing that we did with decimal numbers. When you subtract these numbers, you do a fundamentally different algorithm than when you add. And if someone says in decimal, I want you to compute 217 plus negative 45. If someone gives you that question, you actually do this subtraction algorithm. You don't add these and then somehow convert. You actually change the problem into a subtraction one. And so again, computers are very simple machines. Do you want your computer to have to make that decision and say, well, this is negative, and so I'm going to subtract? And remember, if you wanted to do negative 5 plus negative 7, well, that's really just an addition problem. Okay, you're not actually subtracting 7 from 5. You're adding 5 and 7, and then remembering that you have 2 negatives, and so the sum is going to be... So it gets confusing, okay? And it turns out there's a much simpler way to manage negative numbers. And I'm not going to tell you what it is until Tuesday. I'm going to tell you what it is, but I'm not going to talk about it.
It's a secret. It's a cliffhanger. Who knows? That'll keep me up at night.
Okay, it's called Two's Complement.
Yeah.
You've probably heard about it in other classes. So on Tuesday, we'll start off by talking about Two's complement notation of integers and how that does subtraction and deal with negative numbers. All right, if you didn't turn in your homework, make sure you get it before you leave right now. Update it on the it's like 2 days.
This?
Well, desks are too big, so you need to rotate them next to it.
Yeah. I'm not sure about this week.
I know next week we do, but I didn't tell you.
My Iron Game's amazing, but like,
Okay, yeah, no problem. 2.6.
Iron Game?
I can give you the really poor resolution AVI, which I think has the audio, and then you see that there's some. Okay.
Pretty good. Well, I put a bunch of views, so I didn't have some footage, but I got the from 100 yards out, I use it. I feel like they're and just like old men are all fitted. Old men? Yeah. I mean, it's because they got technique this one. It's all about technique. Think about the thickness of it. Like, the way you're swinging, there's a lot of energy. Just kind of force pushing it in there. I mean, if you're able to keep the energy just in the club, then a lot farther without even having to swing that way.
And clubs are, I mean, they're retired, they can go ahead and they can just lift the driving range.
Yeah, I would. Yeah, especially when you're not even playing that.
Probably gather.
Oh, so what you want to do? So you want to figure out something? Like, what do you?
Yeah.
You haven't even started playing. Like, I would be worried about it. I would be worried about those guys out trying. Oh, you have one right now? There's guys that those guys out trying me. Like,
You've been playing for a while, right?
yeah, I'm stuff 12.
Yeah. You play high school?
And then I was football player or something.
Oh, yeah, that's nice.
Yeah, these compliments. It's ridiculous.